Today we're going to look at how to apply linear regression for a data set where we have more than one feature. I think in the last session we had only one independent feature and one dependent feature. So we applied ordinary least squares and linear regression, and then we also saw some visualization of how to see if the assumption is really holding good or not. So today we'll be looking at one similar data set where we have this data set is bought from Kaggle. I think you can easily download from this link. But however, what the data set is trying to see is over the span of years, what has happened to the life expectancy? Did it grow or was it going down, and so on? So just let us go and look at the data once, then I'll explain you what the process is like, how we apply models and all. So this is what the data set looks like. We have a lot of columns. We have a column like country, what is the year at which this record was, this instance was recorded, and then we have whether it is a developing country or a developed country, and many other columns. Like this is our target column, and we are trying to find out what is the average age that we can expect given the region from where the person belongs to, and it can belong to both male and female. So we are not talking about gender here. And then we have a couple of other columns like the adult mortality, the infant deaths, and the alcohol. So I'll explain you about what all these features are. And more or less, like all of them are continuous features. Okay, most of them are continuous. And if you have already identified, I think we have country as a categorical column. Of course, year is a time series, but for now, in this case, we'll consider it as a categorical column again. And develop status is also a categorical column. Okay, and then I'll explain you about what is the process like if we have to go and apply some models on a particular data set. Then what is the process that we have to follow? So step one is to really understand what we're trying to solve. So what is a business problem like? This is a step one. And step two would be your data. I would say data collection, and then probably some pre-processing steps. When I say pre-process, this is where you have the visuals, and then you have the distribution, and then converting the categoricals to continuous, and then probably we will have split the data to independent features and dependent feature, and then probably go and train the model. More or less, you can divide, like, and let us say that we have like 5 crucial steps that we follow, and the most important things are, I would say, this part where you collect the data, pre-process the data, and probably do some ED analysis. Okay, we'll see if we can do anything of such kind of in this particular data set. This is a very simple data set. We will deal with outliers, and we'll deal with null values, handling the null values and all. So just hang on, see if we can continue, hold on to this video for till the last. Okay. So to begin with, I have already written the code to cut short the time, because simultaneously writing the code would make the video pretty lengthy, and you will get this video in the Git URL. I think you already have my Git URL. If not, then I'll just show you. Just go to GitHub. Yeah, it took a while, but anyways, I found out this is the link wherein you can just find my Git URL. I can just keep it handy here, just in case if you want to reach out to this. And maybe from this, you can look for a file name called Regression. I will upload this in a while once I complete the video. So to start with, we will be importing all the necessary libraries. We'll be using pandas for converting a CSV file to a memories data frame. And then we have a couple of other variables, like a couple of other libraries like matplotlib and cbon for visualization. And then for pre-processing, we have sklearn. I think in the pre-processing, we would be using both standard scalar as well as label encoder. think probably you can just convert this as label encoder. But anyways, and then we have the train test split, which I said, like, once you have the data pre-processed, then you will be converting this to train and test. 80% of the data would be sitting in the train, and about 20% would be sitting in your validation. And then we go and apply our models like the OLS model or linear regression model. And once the model is ready, then probably we'll go and apply the validation. I mean, just have to check how good the model is performing. All right. So let's begin. We'll go ahead with importing the necessary libraries. So just one change I'll do is I'll say label encoder. Yep. And I don't have to have this line here. Okay. And this is what we imported. And hopefully I have all the libraries installed in my local machine. So just in case if you do not have any libraries installed, probably you'll have to do the pip install followed by the library part. And as I showed you the file already, my file is sitting under data. And in data, I have something called as life expectancy underscore data.csv. So I'll be using pandas library to load this data frame into my memory. And this is how the data set is looking like. Okay. Uh, just again, the life expectancy is our target column. So this would be a supervised machine learning model. And we are expected to build a model given the country and all these features. We have to find out what is the tentative life expectancy of that particular record. Okay. For this is a very small data set. We have close to 3,000 records. As we dive forward into this course, we'll pick up more and more complicated data sets so that you don't get comfortable. The more complicated data you take, then it'll be it'll be very difficult for you to consume. Like that should be the way we learn. If you keep learning simple things I think then once you go and face the real world data, then it'll be very hectic for you to solve it. Okay. So first thing what we're trying to do is we are trying to look at how many null values we have in the data set. And I think we already discussed this in the pre-processing video. If you want to look at how many null values are present, you can just go and see dot is null followed by sum. So then it will tell for each column how many null values we have. So in this case, actually, we have 10 records which are null for the ground truth. We do not know what is a ground truth for that. There is one way, like we can keep these 10 records in what you call the train. Sorry, this 10 records we can keep it in the validation set, and the other part we can give it in the training. That is one option, or else maybe you can just impute and see. For now, I have imputed, so let's see how we handle the imputation. Okay, and this is the data types type. We have country as an object, and rest all of them are in okay, even status is an object, and rest all of them are in integer or float. In the beginning of the video, I already said that we will have to consider year as as a category column. It's not a continuous column. Okay, and many other columns, and then we have most of them are float. There are a couple of columns which we need to go and look at. So status is whether a country is developed or not, followed by life expectancy. This is what the target column is. We have to find out what is a life expectancy. And then we have something called as adult mortality. It is just a probability of dying between age of 15 and 60 for a given 1,000 records. So if I take 1,000 random persons who are aged between 15 and 60, out of the 1,000, how many died between this age, and then that is the adult mortality rate for a given country, followed by same like infant deaths also. For a given 1,000, how many infant deaths was recorded, and per capita what is the alcohol that is available in that particular country, and what is the percentage expenditure on health. So this probably could be the measure of people paying for the insurance and all, and probably the hepatitis B and measles and so on. Okay, there are many other features, but I did not go deep into all of them. But if you want more information on this, probably you can just go into this particular link which I have given, the Kaggle datasets. It's one of the good platforms for you to practice various models. Okay, and then we can go and describe the data. So when I go and describe, I will get to see what is the distribution like. Say, for example, if I go and look at adult mortality rate, my median is present at 144, the mean is present at 164, minimum is 1, maximum is 723, and so on. And I can also see if it is a categorical column, I'll see how many unique values are present. And then, of course, when it is category, you also see what is the top. This is nothing but our mode, and what is the frequency like. What is the frequency of this developing? It's like 2000 to 426 and so on. Like, this is what the describe would give. And these are the columns, because the columns are having some hyphens and spaces. I decided to just rename those columns. I simply said, like, I gave a new names to the data frame. I said data.columns is equal to all of this. We also have some syntax like data dot rename, and then we have columns equal to, wherein you specify old column colon new column. So this is one of the way we can rename. I would say syntax to rename columns. Okay, and probably you will have to say in place equal to true. But anyways, like, that is one way. Again, I thought, I felt like this is more easier to do, so I wrote this particular code. And if you have any doubts about this in place, I think we discussed this, when we discussed about list. Say, when I say I have a list equal to 1, 2, 3, and if I go and say list dot append 4, this is the right way. So I can say print list. This is the right way. It will go and append it. But when I say this, okay, ls equal to, and when I print ls, this will become empty. This will become none. Similar to that, it's not exactly the same, but similar to that, what it does is, when you use in place equal to true, all the changes that you made on this new data frame will be stored in the same variable data. Okay, and if at all you're not using this in place equal to true, then you will have to use something like this. You will have to use data equal to this and remove this in place equal to. Either this or that. You're not supposed to use both of them at once. Okay, if you have an equal to sign on the left, then in place should not be present. If you do not have this, then probably in place should be present. Okay, let's move forward. Now I have renamed the data. Now this is how the data set looks like. Okay, it's the same data, just the column names have changed. And then let us pick one column. Now let us handle all the null values. To first handle the null values, first we have to find out what are the null values that is present. Say, in this column, I have 10 null values. Because this is ground truth, I can have these 10 columns in my validation, my testing purpose. Okay, but for now, we are not dealing with we are not at a complicated stage. So only for learning purpose, what I'll do is I'll try to replace this 10 values with maybe the mean, or maybe based on the mode. Now in this case, it is a continuous column, so I'll be going with mean or median. So before going and replacing, it is always good for us to go and check what is the distribution like. So if you want to go and check the distribution, there are two things. One is kurtosis, or we have to go with skew. For now, I'll go and deal with skew. Based on the skew, I'll go and replace it. Okay. Now skew is only to identify if the data set is uniform or not. If it is uniform, then you can go with mean or median. If it is not uniform, probably then you have to go with the median as compared to the mean. Okay. So if I look at the KDE plot, I would not say this is normal, because the normal would be a perfect bell shape. And I have told us many times, like, in real world, probably you will not have a perfectly normal data set. But for now, I think this is almost, I would say it is almost okay. But just in case, if you want to go and replace it, it is good to go with the median values than the mean values. Just like how you used matplotlib, you can also use cbond to get the same graph. It's just the thing that the axis is little different. That's why you see a little change, but more or less it's the same data, so you don't have to worry much about it. And if you want to just look at what is a median, so we have the mean at 69.2 and the median is at 72. It's almost okay. Like the center is like there is not much skewness around in this data set. But because we're discussing about this uniform distribution, I just want to recollect, this is how a uniform distribution would look like. It's perfectly symmetric on the left and perfectly symmetric on the right. And just in case if you have a lot of data on the left, then it is called as right skewed. So whenever I say it's right skewed, it means that a lot of data is present on the left and there are a lot of outliers on the right side. Outliers on the right side, right skewed. Similarly, outliers on the left side, left skewed. Okay, so our target now is more like a left skewed data. Our data is like this. So the median is present little far away from the mean. Okay, let's see if that is the case. Yeah, the median is present little far away from the mean, 70 to 69. So that is what the graph is saying. The median is present towards the right side. Now what I would do is, like, one way is to go and handle one column at a time. Okay, which is the right way to do when you're learning new concepts. But as we move forward, it is always good to automate this. Like the more you automate, the more you learn. So now what I'll be doing is I'll try to write one function wherein I handle all the null values by just checking what is the skewness. So I already found the skewness is, in this case, is 0.6. And if the data set is normal, the skewness will be very close to 0. If the data set is normal, the skewness will be very close to 0. And if it is not normal, obviously you will have either towards a positive sign or towards a negative sign. Okay, just keep that in mind. Based on the skew value, I'm going to decide whether I have to go with the mean or I have to go with the median. Okay, this is step number 1. And step number 2 is I'll be using box plot to identify if there are outliers or not. And then we have already discussed about quantiles. So in pandas, if you want to go and look at a quantile, like this is how you do it. You have a data frame, you have a column, and then you specify which quantile you want. So in this case, I want the 99th quantile and the first quantile. When I go and run it, I get to see what is my 99th quantile value, it is 6, and what is my first quantile value, 45. One simple method that we can do to remove outliers is any value that is beyond this 86 can be replaced with 86. And any value which is lesser than 45.6 can be replaced with 45.6. This will cap the outliers. You're not dropping those records which are having the outliers, but you're capping it. Okay, so I'll show you in the graph in a while, but just keep in mind that any value that is present after the 99th quantile, you're simply going and replacing it with this 99th quantile value. Similarly, the first quantile, any value that is present lower than the first quantile, you're going and replacing with this particular value. We will have to do this only for those columns which are not normally distributed. If you find that there are any outliers, only then you're going to do this. Okay, but for now, I think we'll just try to write one simple function. So this is handle nulls. I'm pretty much writing the same code what you found earlier. Okay, so you have already seen this, wherein I tried to use cbond to plot a particular column. So this is the code. I took one column. This is my data frame. I took one column and I made this as a function. So in my function, first I'm going to plot. The moment I get a data frame, I'll take one column, which is a continuous column. And for that particular column, I'm calculating what is my skew value, what is my mean, what is my median. I'm just printing it. Okay. Followed by, I'm just going to print two graphs. One is the KDE plot. One is the KDE plot, and second is my box plot. Now, box plot, if you remember, it is to show the distribution, how the distribution is like, and if there are any outliers or not. If you have more concerns around this visualization, I think you should go and check our session on visualizations from in Python. I already done this. So you can go and do like univariate analysis and bivariate analysis and multivariate analysis and so on and so forth. So if you want to apply that, probably you can. This is a good time for you to copy the code from this particular thing and just get into this and replace the data frame and column names and to find those graphs. But for now, I'm not going to deviate because our intention here is to apply linear regression. So let's stick to it. Just in case if you want to go and use visualizations, I think this is the point where you have to find where you can find the code. Okay, and now I have plotted two graphs. One is the KDA plot and one is the box plot. And then, as I said, like based on the skewness, if the skewness, the absolute skewness is less than 0.5, I would say it is almost normal. If it is not 0.5, I would say that I have to go and replace the null values with the median value. So my previous recording, we're also discussing about this dot log and how to subset a data frame and how to replace the values. I think I have covered all of them. So I assume that you already know all these things. Okay. And then this is the place where we'll go and replace the quantiles. So any value that is greater than the 99th quantile, I'll replace it with 99th quantile. And any value which is lower than the first quantile, I'll replace with the first quantile. Okay, this is one simple function wherein my input is a data frame, the column to which I will be doing these steps, and if I have to replace the null values or not, and if I have to cap the outliers or not. Based on these conditions, I will be doing all this process. Okay, I think this is very simple. So let's run this. And I think you already know the doc string. This is what the doc string like. And I'll just go and apply. For now, I will say I'll impute the null values, but I'll not replace the outliers. So when I go and do this, you can see I have 10 null values. Because I said impute null equal to true, all these null values may have been replaced by now. The mean is 69 and median is 72. I think we already saw this. And this is what the box plot looks like. If you notice that we have all of these, I think I would not say that all of these are outliers, but only to some extent we will be replacing them. Maybe probably this. Any value that is far away after 99th quantile, only those values we are trying to replace. Despite this, if you still find that it is not normal and I want to process this, then we can go and apply transformations. Now, there are many other transformations. Maybe you can go and apply a log, maybe you can apply a square root, any polynomial, anything that you want. See which distribution, which function can convert this as a normal distribution, then that would be fine. But keep in mind that I would not change my target column. This is my ground truth. And if you change this, it might not show you the results that you already wanted to see. But in this case, I'm just trying to replace only the null values. And there are a couple of outliers. So I'm just trying to confine my model to a precise location. Let us say that this is our bullseye and there are a couple of outliers in and around here. So I'm asking my model to look at only this region. So these regions can be ignored. So we'll talk about this. What is bullseye? What is this region? There is something called as bias, variance, overfitting, underfitting. So probably for tomorrow's class, I'll be looking at this. But for now, just keep in mind that we are trying to do this so that our model can precisely look at a particular range of numbers. All right. So now let's go and do the same thing with adult mortality. Now, this is how the adult mortality looked like. I did not impute the null values yet. You can see the impute null values is false and the cap outliers is also false. By default, they are false. So if I do not pass these variables, by default, they will be passed. They are called as keyword arguments. And then what I'll do is I'll try to go and replace and see. After replace, what is the change like? So I have imputed the null values. I have capped the outliers. Do you see much change? I don't see much change, but yeah, 1 minute. Adult mortality 144, 169. Yeah, I don't see much change. Only thing is that maybe some part of this has changed. Now let us see one more time. Yeah, So after the change, what is has given us is like it has changed to 1.04. It is not still normal, but it's okay. Almost there is a lot of data set on the left. It is right skewed, but we can deal with it. We don't. I think we can also remove a couple of more variables, but if I want to automate, then it will be very tricky. I cannot know what this cap value should be. But for now, I think 99th quantile should be the best bet. Okay, like this, what I'll be doing is I'll try to replace all such columns which are continuous. All these columns are continuous. Now you already have a function which will do all the steps for you. So I'll simply go and call it in a for loop. When I call it in for loop, it will continuously apply for all the columns and it will try to do the same activity. Yeah, I think that is it. So this is what the conversion, like this is after the, like before the conversion, but more or less we have dealt with replacing the null values and capping the outliers. You can see there are a lot of outliers here in this particular column, like for SS for HIV. Yeah, I think it's for HIV. There are a lot of outliers. Even in this case, we have a lot of outliers. I'm not sure what this term means to us, but like we have a lot of outliers. And here also we have a lot of outliers. But anyway, we have dealt with replacing the null values and also replacing some outliers. But if you still want to go and pre-process them to some more extent, we can try it. I would not say no to it, but you can try it. Now, after the imputation is over, now I see that there are no null values. Okay. And now, till now, we have only dealt with replacing null values and outliers, right? Now, what is the next step is like you have to convert the categorical data to numerical data. Now, when I say categorical data, it is like object columns. These object columns can be converted to numerical in many ways. Now, what are those ways? First is you can convert them as label encode. And second is probably one hot. One hot is also similar to pandas dummies. Okay, first I'll tell about label encode. Say, let us say we have a feature. The feature name is say maybe I can say maybe name of a person, and we have some names here: A, B, maybe A again, D, X, maybe Z, and so on. So what this label encode would do is it would assign each category a number. So you can imagine that we have a dictionary. A will have 0, B will have 1, C will have 2, and so on. Maybe Z will have 26. Okay. Once it converts this, it identifies that, okay, these are the different features that I have. So for each feature, it will be naming one number. So wherever it finds A, it will put 0. Wherever it finds B, it will put 1. A again 0, D is 4, and so on. Maybe this is 26 and maybe this is 24. Okay, like this. It will convert all the numbers. It will convert all the characters to numerical. This is what the label encode. The shape will remain same. Shape will remain same. When I say shape, the number of count, let us say it has like 400 records, it will still remain 400 records. There is no change. And let us say there is only one column, you'll still see one column here. Okay, this is about label encode. Now, when you go to one hot encode, let us say we have a feature, direction. Okay, I have north, I have south, I have east, I have west, maybe north again, maybe north again, maybe south again, west again, and so on. When you apply one hot encoding or get dummies from pandas, what this would do is like it will create 4 features because there are 4 distinct categories. It will get converted to 4 features: north, south, east, west. Now, because it is north, this will be 1 and this will be zeros. Because it is south, this will be 0, this will be 1, this will be zeros. And because it is east, this will be 1, and so on. You can imagine now. This is what the one-hot encoding or pandas get dummies would be doing. There are a couple of problems that we come across when we deal with this. Okay, just keep this in mind. This is a very important topic. Okay, very important topic, because you might see this error many times when you are very new to data science thing. When we are applying any model, let us say that I go and apply linear model, and as I said, I follow a couple of steps. And in the fourth step, I said that my data will be divided to x and y. This x and y will be divided to x train, maybe x val, and y train and y val. I don't have space for that, but okay. So what would happen is you have x train, x val, similarly y train and y val. When this process is applied to convert the data from categorical to numerical, let us say x train had 4 different directions. Okay, it had only north, south, east, and west. Your one-hot encoding or pandas get dummies would be converting this one feature to 4 different columns. Whatever we discussed earlier, it converts to 4 different columns. But in your x, when it comes to x val, it has one new feature, new category called as new northeast, and it also has something like southeast, let us say. So when it sees some new category in this x validation, it doesn't know what to do with that, and it will throw out an error. New class identified which was not seen earlier, something like that. So what you will have to do is, one way of dealing with that is you can apply this transformation combining both the train and validation. You can go through with the model, but again, when you have some unseen data, this can become a problem again. Maybe this northeast present is maybe instead of northeast, maybe it has got southwest. The southwest was not present in X validation also. This again will throw error. So what you'll have to do is, like, once we have this one-hot encoding, any category that you find other than this, you will have to treat it as others or ignore it. How to ignore it? Simply drop that column after the conversion. So let us say in the test data set, you had columns like north and southwest. So when you apply get dummies, what would happen? You can apply one column for north and one column for southwest. Because this southwest column was not present in your X train and X validation, even if you pass it to the model will not use this as an input. So it is good for you to drop this feature. And what are the other things? We had a couple of other features like south, we had east, we had west. Create one empty columns with 0 values here. Always keep that in mind. Probably in this data set, you did not see it, but this is a very important error that you are going to frequently observe. Okay, for now, you don't have to worry about it, but whenever you see such error, I think you can easily recollect what I have said. Okay, let's move forward. Now, as I said, like, we will be converting to X and Y. So first thing is, like, I have my categorical columns. Now year is category, country is category, and status is category. I have seen the distant columns, and there are so many values. Probably year is like ranging from 2015 to 2000 and many different countries. And status is having only 2 values, developed and developing. I think we don't need this. Okay. And now what I'll be doing is I will be importing, I have already imported label encoder. I will go and apply label encoder on both my columns, my year column and country. So what it will do, it will try to look at the distinct features and it will apply one new number to it. As simple as that. You simply go and fit underscore transform on the whole column. Similarly, for status, I have seen like whichever I said like whichever is developing, I mark it as 0, and whichever is developed, mark it as 1. And this column is then converted to category. Now, because this is an object, we cannot pass objects to model. I'll convert this to category. So once this transformation is over, you can see what is the data set look like. Now the country is having numericals, year is having numericals, and then status is also having some numericals and all of that. Next is like we will segregate into X and Y. My target column is life expectancy. So I'll be keeping only life expectancy in my Y, and I'll be dropping this column from my X features. Okay, this is what the X and Y is. And now what I'll be doing is I'll be applying. Now, if you remember from our previous sessions, we will have to get all these continuous columns to one scale. Now, the scale of infant deaths is different. The scale of alcohol is different. The scale of the expenditure is different. All of them are different, right? So in order to get them into one scale, we will be using standard scaler. And I'll get all the columns which are continuous. Okay. So I'll exclude those features, which is my ground truth, and which are category. I'll not touch them, and then I'll go and apply standard scaler. So for applying standard scaler, it is simply go and call the standard scaler function, do a fit on these features, and then you do a transfer. It is pretty quick. The data is very small. So once the transformation is over, we have converted all the categorical features. We have converted all the numerical features, and now we should be good for splitting the data. Now, once you go and split, we can use train to split library again to convert our independent features and dependent feature. I'll say 80% should be my train set and 20% should be validation. Now, validation is the one which the model is not going to see. Okay, we are protecting this data to test the model, how well the model is performing. Okay, and we will use this data set for testing purpose. Now, once we have the train and test, I will go and see what is the shape like. You can notice that the shapes are pretty much same. We have 2350 records in X train, 2350 records in Y train. Similarly, 588 records in validation and 588 records in validation here. Okay, now this is the time for us to go and apply models. Now we are done with all the pre-processing steps. The null values are treated, the outliers are treated. We have converted the categorical features to numerical features. We have scaled the numerical features, and then we'll apply simple linear regression. Now this is the ordinary least squares. Simply, we have imported the ordinary least squares as SM stats model, and I'm applying it. So once you print the model summary, you get to see what is the R square and adjusted R square. I think it's pretty good. We have a probability of F statistic less than 0.05. So statistically, it is also good. And we have many other features. Okay, this is how the multiple linear regression would be performing. Similar to ordinary least squares, I can also go and apply our linear regression model. So this is how you use a linear regression model. You simply declare a variable as a linear regression model, and you fit it on X train and Y train. So once you fit it, this model will be calculating all those patterns. And once the patterns are fit, now we will go and make the predictions. Now, model is from ordinary least squares. Lin model is from linear regression model. Okay, and I will be predicting both the unseen data and seen data to see how the model is behaving for both the records. And once we have it, the prediction is pretty done. Now we'll go and validate how the model has performed. Now this is very important step for you to notice, like how was the model predicting on a seen data and how was the model predicting on an unseen data. Okay, so the ordinary least squares was making like close to 25 root mean squared error. So both train and validation have a similar error type. So I think the model is pretty good, but let us see how the linear regression has performed. So linear regression has performed much better. So ordinary least squares is like for like little less complicated as compared to linear regression. So linear regression has performed much better on that particular data. Okay, this is how you can apply linear regression. Of course, most of the part is around pre-processing, or I would say analyzing each column at a time and seeing what can be done with that particular records. Like if you have to deal with this outlets, how should we deal with it? If you have to deal with null values, how should we deal with that, and so on. So these are the things that we'll be doing for applying any model. So as we learn new models, all the steps remain same until the point where you come to this place where you split the data to extend and xval. Okay, then you keep applying different models. Like in this case, I applied least squares, ordinary least squares, and then I applied a linear regression. Similarly, maybe you can also apply addition trees, maybe you can apply random forest, maybe light gradient boost, and so on. So the pre-processing step remains same for all the models, unless you're trying to go to some models like time series and all, wherein you have to deal with lags and all. But given that it is a structured data, the pre-processing will remain same for all the data, all the models, and you can keep trying different models and see which model is really giving you the error, very good at error metric. Say in this case, like OLS has given 25, but on the same hand, for the same data set, like linear regression was giving much better RMSE. Lower the RMSE, better as a model. But again, as I said, like the error that you see in the train data and validation data should be almost similar. Like in this case, it's pretty much same, 3.97, 4.02. It's not much difference, I would say. So if you see similar errors, then your model is good. But there might be a couple of cases wherein you see that in train the error is like 2.5, but in validation it comes to like 12, maybe 20, maybe 5, whatever it is. So if the difference between these two error metrics are far away, then there is really some problem in the model application. Maybe the model is not trying to find out those patterns which it should really find. There are a couple of terms that we define for this. This is a point where we call that the model is overfitting. Usually you will see it in decision trees, but I'll tell you, let us not go to that point now. Just keep in mind for now, wherever you're trying to apply a linear regression, have a similar error metric in both trained dataset and validation dataset. If the error metric remains same, I think we should be good with the model. Of course, the error should be as low as possible. As compared to 25, 3 is quite small. So I would go with linear regression for making the predictions on life expectancy. Okay, I think that's it for today's session. I will touch base tomorrow with some new concepts. Thank you.